I'm with Dan McCammon's sounding rocket group at the University of Wisconsin in Madison. So I'd like to talk to you about our new sounding rocket payload that we hope to build for studying the X-ray emission from diffuse hot gas. And we could not build such a payload without our long-term collaborators, in particular the ones listed here at Goddard Space Flight Center. But I should also mention that the new microwave MUX readout we hope to use will be provided by the group at NIST. And Kelsey Morgan happens to be one of our former graduate students, and she has firsthand experience with the excitement of working on rocket experiments. Next slide, please. All right, so let's talk very briefly about the science motivation and how that translates into the technology requirements for our instrument. So from our current understanding of the universe, we think that about half the normal matter is in hot gas at temperatures of about 1,000,000 degrees or higher. And it would be great to actually observe that and to resolve it spectrally to see what it's made of and see how hot it is and where it's located. And so there's really four key ingredients we need to do that. So first of all, because the gas is such low density and the emission is faint, we need a really high throughput instrument. And that throughput is detector area times field of view. And then we also need to have really good energy resolution so we can identify the individual lines and ignore the ones where we don't really have good atomic data. And that also requires 2 eV or maybe better 1 eV spectral resolution. And then the galactic foreground is so much denser than the intergalactic medium filaments and the extended CGM around the galaxy. So even though there's far less gas, it's still 100 times brighter, and it's also emitted in the same spectral lines. So then if you want to detect those faint lines, you need basically to use the separation via the redshift. And that is the second reason why we need this really high spectral resolution. So with these two requirements already, we're ending up in the area of energy dispersive detectors. Just specifically, we plan to use transition edge sensor microcalorimeters down at 50 millikelvin. And so our next requirement then is that we need to calibrate those detectors in flight, and that's not as trivial as you might think. And lastly, we also have to then worry about the gain stability, and the TSs are very sensitive to the environment, in particular magnetic fields and also temperature, of course. Next slide, please. So the 2020 Decadal Survey listed mapping the IGM and CGM as one of its top science priorities. But as much as we love our sounding rockets, we just don't have enough observing time to do that job. So that'll be up to a future major satellite mission to do. But that mission, will also need the same kind of technologies. So we can try to get a head start on that. So at 600 eV, the payload we're designing would have a throughput of about 26,000 times greater than what the XRISM satellite can provide. And that's, if they can get the gate valve door opened this fall. And we'll keep our fingers crossed for that, of course. So the 5-minute observing time of our sounding rocket would be enough to get a nice spectrum of the bright foreground gas now inside the galaxy. And our first science target would be the local hot bubble, and that's a cavity surrounding the sun filled with gas at 1,000,000 Kelvin. And the spectrum here on the right shows a 250-second Monte Carlo simulation of 6-component spectral fit to many of the previous observations of that field outlined in white on the Rosette map here on the left, and that's a 60-degree field of view. And this assumes, of course, the target resolution that we'd like to have and also the high throughput of our new rocket instrument. And you can see that with 1 eV resolution, we should be able to identify a lot of the different emission lines from the highly ionized gas and hope to use these fingerprints to tease out some of the information about the different components. And note also that all the interesting stuff is below about 1 keV here. Next slide, please. All right, so let's talk about our detectors a little bit. The optimization here is quite different from those that you would use for a general purpose observatory, and they want usually much smaller pixel with higher energy range, and that's a separate development effort. So for us to maximize the throughput, we'd like to have the largest possible detector size. i.e., really large pixels and as many of them as we can get. But, unfortunately, when you make the X-ray absorber larger, the heat capacity, C in that equation on the right, goes up and the energy resolution degrades. So how big can we make them? Well, to absorb 90% of the X-rays below 1 keV, you need about 200 nanometers of gold, and that's it. So then, to get to the 1 EV resolution, we can probably make the detectors about a millimeter in square. And the plot here on the right shows contours of that predicted energy resolution against parameters. Thermometer sensitivity is on the x-axis, and the noise parameter of the TES is on the y-axis. And so the points on here basically illustrate that we can fabricate those kind of transition edge sensors, and they will achieve the required performance. But now back to the absorbers for a second. So if you try to visualize what they would look like, their aspect ratio is really similar to kind of a sheet of letter paper. And so if you'd like to connect those absorbers to the TES only that sits underneath so that the thermal energy goes right to the thermometer, well, then you need to support that paper in a single point in the middle. And well, you can see it would just sag under its own weight. So we don't want that to happen and to have the absorbers collapse onto the substrate. So how can we make them stiff enough to keep them flat? Next slide, please. All right, so here's the scheme we have for that. Basically, you need to fold your paper and or your thin sheet of gold. So if you make the folds all along one direction, then you can make it stiff against bending in that direction, but it gets weak in the other. So really, you need to make this 2D system of folds, and that's shown in these micrographs here. If you have some trouble visualizing it, you can kind of think of it as a waffle pattern, but perhaps even better, an egg carton has kind of a similar geometry. So with the help from our colleagues at Goddard, but also our graduate students, Ambush and Miriam, they have really figured out how to make this work with the thin 200 nanometer gold films. And these absorbers you see in the SEM images are already 1 millimeter square, and they're suspended only 3 microns above the TS. They curve up in the corners a little bit due to residual stress, but we've gone through this process a few times now, and we find that this really works reliably. So next slide, please. Okay, so I briefly need to talk about the readout. The key ingredient here to get the number of pixels up is the microwave squid mux that technology was developed at NIST. And the trick is to upconvert our kilohertz bandwidth calorimeter signals into the microwave range using these RF squids and microwave resonators on a feed line to pack, 500 or more channels even into a single microwave line. And that saves us really a ton of wires that would otherwise be necessary with, more conventional schemes like time domain multiplexing. And it really reduces the per channel cost since the readout at room temperature can now also be done with just commercial FPGA electronics. And yeah, so we hope to get this off the ground, and that would be the first microwave squid mux in space that we know about. And I think the folks at NIST will be quite excited if that happens to pass. All right, next slide, please. Okay, now we need to talk a little bit more about gain stability. So the TESs and the squids are, of course, terribly sensitive to magnetic fields. And we need to ramp the field in our ADR up to 4 Tesla before the flight so we can cool the detectors down to 50 millikelvin later. And for that situation, we need to shield against the stray field of the magnet to avoid trapping flux in the squid mux. And the goal here is to keep the field below 5 microtesla or so. But at the same time, we need, several infrared blocking filters in front of the detectors. And with our large field of view to keep, the size and cost reasonable, we need to put those as close as possible to the detectors. And further, we need to keep the shielding assembly really close to the magnet to improve the rigidity of the 45 millikelvin stage and minimize any vibrational heating during launch. And our grad student, Sophia Novak, has been developing our shielding design with numerical simulations, which is shown on the right here. And her design makes use of two bucking coils and then a combination of mu metal and superconducting shields. The superconducting shield is actually made out of two nested cans, and that allows us to assemble the shield without having to make a superconducting solder joint. And then the other key innovation here is that we can complete the superconducting shield with a superconducting mesh in front of the detector phase. And that allows us to get the 2K filter quite close to the detectors. And without it, we would need, a very long open shield and huge filters to accommodate a 60-degree diameter field of view. And Sophia's simulations show that we should be able to achieve this and get less than about 1 microtesla with the ADR magnet at full field. Next slide, please. Okay, now in flight, we'd be regulating at 45 millikelvin. The stray field from the magnet will be much less. But now, the TES gain is very sensitive also to small magnetic field changes on the order of, 0.1 microtesla or so. So Sophia has checked how well her design shields against changes of the order of Earth's field here. And the plot on the left is for horizontal field change, and the one on the right is for vertical field. And she discovered that by adding another flange to the front of the mu metal shield, we get another 40% improvement in the shielding against horizontal fields. And then the overall field excursions that we expect at the detectors are below 0.5 microtesla for pitch or roll maneuvers. And that's probably manageable, especially if we can track the detector gain in flight, as we will go over later. Okay, so next slide. All right, so we're also working on sort of a complementary or maybe backup approach for on-chip shielding. And that idea goes back to some work done by David at Esron and others before him at Goddard. And the trick is to put a superconducting layer just right behind the TES, which is suspended by that thin silicon nitride membrane. And one thing that's different in our implementation is that we only put the superconductor behind the individual TESs and not across the whole chip. And then it's energetically much more favorable to expel the field from a small area. So in the plots on the right, you can see how the current through the TES varies with the applied magnetic field. And the device with the superconducting ground plane, that's the one on the right, is much less sensitive to magnetic fields. And you have to point out here that the scales here, the vertical and horizontal scales on the plots are quite different. And so we've also seen that there's a little bit of a larger scatter in the optimum field for the devices with the ground planes. But because their field sensitivity is so much smaller to begin with, it looks so far like we'll still come out ahead in gain sensitivity, perhaps by a factor of 30 to even 100. And so with just adding this one very simple fabrication step, we get a significant margin on the magnetic shielding requirements. Next slide, please.
Felix, 2 minutes.
Yeah. So with all that out of the way now, you can see it's really important to have calibration and gain tracking in flight. And the big challenge here is that the X-ray fluorescence lines are much wider than the energy resolution of the detectors. So a couple examples here are carbon and fluorine. You really need a lot of counts to use these for an accurate calibration. But of course, that's no good. And you can't check energy resolution of the detectors with lines like that. So our solution here is a pulsed laser calibration source. And the neat thing about the calorimeters is that they measure the deposited energy, and they don't care if that came from a single 1.5 keV X-ray or from a short pulse of, 500 3 eV photons. But you need a detector that has high enough energy resolution, and it gives you a spectrum like shown on the right. And you can make these square root n wide Poisson distributions and center them wherever you like. And then you only need a few counts to determine the gain accurately. Since you also know when the pulses arrive, you don't lose observing time, and you can take calibration data continuously during the observations in flight. All right, next slide, please. Okay, so you may be wondering if what I said about the response to X-rays and photons is actually true, and our graduate student Avro Roy checked that. And, we have here on the left, you have a spectrum that shows in blue the optical photons, and then in red the true X-ray events. And then we compared that, and basically we find that we can establish that energy scale to about 0.1 eV, and it agrees to within 0.4 eV what the aluminum K alpha line should be. And, then we can also get directly the detector energy resolution out of this, which is about 1.7 eV. And that's a real game changer for us, and it's better than what we need for the rocket experiment. But it would also be really useful for an X-ray emission like LINX, and if we can push this out to 10K eV. So our graduate student Sophia has an NSTRO fellowship to investigate that. Next slide. So we're working on payload design, so I'm not going to go into that. There's previous history, of course, with the Wisconsin XQC payload and also the MicroX payload that was based on our design and developed from there at Northwestern. Okay, so last slide then, please. Yeah, so here's our graduate students, and I think I've kind of explained how we have pretty promising solutions to the challenges we have. But hopefully this will also be useful for a probe class mission to attack some of the major objectives of Astro 2020. And we hope that our graduate students will be able to carry their excitement forward to work on future missions at NASA or elsewhere. Thank you.